In this video, we will discuss the different interconnection techniques used for solar cells. In order to fabricate a PV module out of an example of solar cells, there are different ways to electrically interconnect them. The technique used depends strongly on the PV technology in question. In this video, we will discuss the connection in conventional crystalline silicon technologies, and in the next video, we will discuss other interconnection techniques. The interconnections can be roughly divided into three groups. The most widespread and mature group is the conventional crystalline silicon technology. In the next video, we will discuss an alternative technique for crystalline silicon PV modules and the monolithic integration of solar cells, the technology used for thin film PV modules. Solar cells can be connected in series and consequently the voltages add up. For example, if the open circuit voltage of one cell is equal to 0.6 volts, then a string of three identical cells will produce an open circuit voltage of 1.8 volts. At the front side of a conventional crystalline silicon cell, we can usually find a silver-based H-grid, named after its particular shape. The two widest metal strips printed on the cell, also called bus bars, represent the arms of the H, and the other perpendicular thin lines are called fingers. On the rear side, a fully metallized area is usually realized. In case of bifacial PV modules, the rear side does have a second H-grid. On top of the H-grid, it is possible to solder the so-called tabs. This is usually done using a less noble material like copper. These tabs are thin interconnection strips that connect the front side of one cell to the back side of the next cell. In this way, the series connection between the crystalline silicon cells is performed. It is important to note that for series connected cells, the current does not add up and the current of the whole string is determined by the cell that delivers the lowest current. Hence, the total current in a string of solar cells is limited by the cell producing the lowest current. The second way to interconnect the solar cells is in parallel. In case of completely identical cells, the voltage of the module remains the same, while the currents of the solar cells add up. In short, the black line depicts the IV curve of a single solar cell. When we connect two or three solar cells in series, the result is the blue line, where the voltages add up while the current stays the same. In case we connect, for example, three cells with the same IV characteristics in parallel, indicated by the red line, then the current becomes 3 times as large, while the voltage remains the same. When we consider a series connection at module level, we may end up with this 36 cell structure. This module has 36 solar cells, but nowadays it is also possible to find different types of modules that achieve high voltage levels by interconnecting 60, 72, or even 96 solar cells in series. A high output voltage minimizes the resistive losses, which depend on the current flow through the metallic grids, and enables high efficient operations of the inverter, which we will discuss further on. For some PV systems, the right solar cell configuration depends on application. For example, if you have a module with a high open circuit voltage that is close to the load voltage, then you may avoid the use of the DC-DC converter, which has some conversion losses. So the voltage and the current output of a module can be partially tuned through the solar interconnection. Coming back to this example of 36 cells series connected, once we know the IV characteristic of one single junction solar cell, for example, a short circuit current of 5 amperes and an open circuit voltage of 0.6 volts, then we can derive the output open circuit voltage of the module, which would be 36 times higher compared to the single solar cell. The result is therefore 21.6 volts and a short circuit current of 5 amperes, which is the same as one single solar cell. The switch inside the junction box can also connect several series connected strings in parallel. If two strings of 18 series connected cells are connected in parallel, as illustrated in figure, then the module would have an output open circuit voltage of 10.8 volts, which is the voltage of one string, and a short circuit current of 10 amperes, which exact interconnection is preferable depends on the application. This module, for example, would not be suitable for a 12 volts battery. As solar cells are interconnected, the following step in module production is the lamination, which we will briefly explain using EVA as an example. These are pictures taken in an R&D lab a number of years ago. Nowadays, of course, the production lines are fully automated, but the principle remains the same. In general, there is a backplate where all the cells are mechanically placed. Then the interconnection strips are soldered from one cell to the next. The whole stack, consisting of front glass, encapsulant, interconnected solar cells and back layer, are brought together into the laminator, which is heated above the melting point of EVA, which is around 120 degrees centigrade. This process is performed in vacuum in order to ensure that air, moisture and other gases are removed from within the module stack. After some minutes, when the EVA has melted, pressure is applied and the temperature is increased to about 150 degrees centigrade. During the curing process, a curing agent present in the EVA layer starts to create transverse bonds between the EVA molecules. As a result, EVA obtains elastomeric, rubber-like properties. In next video, we will continue our discussion on the different interconnection techniques for alternative crystalline silicon and thin film modules.